Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 29th video lecture. And today we want to conclude our discussion about continuity and compactness, and also start talking about uniform continuity. Okay, so today we're going to start with the theorem. And what it says is if f bar is a continuous mapping of a compact metric space X into RK, then f bar of X, the output space of F, is closed and bounded, and that means that F itself is bounded. We had the definition of a function being bounded last time. Okay, so we want to prove this theorem. So I won't write down the hypothesis, but what I'll say is that from a previous theorem, we have f bar of X, that space in RK, is compact. And that's by really the previous theorem we have that. Okay? So it's compact in RK. Okay, so by a theorem that we had some time ago, having to do with RK and compactness, f bar acting on X, which is a subset of RK, is closed and bounded. This theorem that I'm referring to was a three-part theorem. It said that the following are equivalent. And compactness was in RK was equivalent to being closed and bounded. Okay? So this is a closed and bounded subset of RK. Thus, as a bounded subset, there exists a p-bar element of RK such that for every y-bar in RK, I'm sorry, I should say here, there exists an and an m greater than 0. M greater than 0. Such that for every y bar in RK, the norm, that's the metric in RK, between y bar and p bar, the difference, will be less than m. Thus, for every x, element of big X, the norm between f of x bar and p bar will be less than or equal to m. And here, where you're thinking of f bar acting on x is equal to f sub 1 acting on x, f sub 2 acting on x, up to f sub k acting on x. Okay. And again, p bar is equal to p sub 1, comma, p sub 2, comma, all the way up to p sub k, as it is an element of our k. All right. So, for a particular I, we have the absolute value of f sub I acting on x minus p sub I will be less than or equal to the sum, as I run from 1 to k, of f sub I of x minus p sub I to b squared, and all this raised to the 1/2 power, which is the difference of f bar of x minus p bar inside, the norm, and that's going to be less than or equal to m. So that gives us that the absolute value of f sub I of x minus p sub I is going to be less than or equal to m, and that's true for all I in 1 to all the way up to k. So, what we have here is that rewriting this properties of absolute values, we have minus m minus the absolute value of pi. It's going to be less than or equal to f sub I of x. Less than or equal to. It's going to be less than or equal to m plus the absolute value of pi. And this is a statement that's true for all I running from 1 to k. Okay. And so here, what we'll do is we'll let p equal to the maximum of all the absolute values of the p sub I. So here's p sub 1, p sub 2, all the way up to p sub k. Thus, what we get is that m minus p will be less than or equal to f sub I of x, which will be less than or equal to m plus p. So I just made this smaller by inserting minus p for minus the absolute value of pi. Likewise, I wrote down something bigger, m plus p, than what's here. So, that says the absolute value of f sub I of x will be less than or equal to m plus p, and this is a statement that's true for all elements, for all I elements of 1, 2, all the way up to k. So we're working on showing that f is bounded, okay? And we're getting very close to doing so. So, the norm of f bar acting on x is equal to the sum as I run from 1 to k of f sub I acting on x squared raised to the 1/2 power. Now, this squaring here, acting on f sub I, is the same thing as, if you would like, the sum as I run from 1 to k of the absolute value of f sub I, x, to be squared raised to the 1/2 power, which I'll say is less than or equal to the sum as I runs from 1 to k. I'll replace these absolute values by something bigger than it, which is m plus p squared to the 1/2 power. Now m plus p doesn't depend on I. So this will be equal to m plus p squared times how many of them would you have? It's k. You take the square root of that. So that's equal to m plus p, since m plus p is positive, times the square root of k. And so what we have is, for every x element of big X, this norm f of x is going to be less than or equal to, here, m plus p times the square root of k. So this is some number that's positive that bounds the output values for each x in the domain for the function f bar. So that means f bar is bounded. I wouldn't say bounded on x, it's just bounded. And that ends the proof. Okay. Next, I want to write down something called the extreme value theorem. It's called the absolute extreme theorem. Now here's what it says. This is something we would see in calculus, okay? It says, suppose f is a continuous real function on a compact metric space X, and big M is equal to the sup over all p's in big X of f of p, and little m is equal to the m of over all p's in big X of f of p. Then there exists a p and q element of X such that f of p is equal to big M and f of q is equal to little m. I said that this is a theorem or version of it that we would see in calculus. What we're used to seeing in calculus is we define f as a continuous function on a closed bounded interval. That makes it a metric space, a compact metric space. And then we'd say, we define it on that closed bounded interval into R, okay? And then we would say f attains its max and min values. And that's what this is saying, but in a more general setting. Okay. Here's the proof. We'll let f be a continuous real function on a compact metric space X. This is just a hypothesis of the statement. And big M equal to the sup over all P's and X of f of P, and little m equal to the infinity over all P's and X of f of P. Okay. All right, the first question is really the existence of these numbers. And so here's what we can say. Note, f of big X is closed and bounded, is a closed and bounded subset of R. Okay. That's from the previous theorem. Okay? And so, in particular, f of big X is bounded above and so that means that the supremum exists, okay, of this set. So script M exists in R. Now, what I want to tell you is that by a previous theorem, we're going to get that big M is contained in f of X. It has to do with the closedness of f of X. Okay, so by a previous theorem, big M is equal to the sup over all P's in X of f of P is an element of f of X. And what does it mean to be an element here? That means so there exists a P element of X. Because what does it mean to be in here? You're an output value of f. That means there's an input value that's sent to you. So there exists a P in X such that f of P is equal to big M. So that's half the theorem. Okay, now, also, f of x is bounded below, because it's bounded, big F of x is bounded. F of big X is bounded, so it's bounded below. Okay, so that means that little m equal to the infimum over all p's in x of f of p exists in R. Okay, so what this means is that for every epsilon greater than 0, remember this is the infimum, so m plus, little m plus epsilon is not a lower bound of f of x. So this was the greatest lower bound, so if you go a little bit bigger than it, it's not, if you go a little bit bigger than it, it's not a lower bound. Okay. So, there exists a piece of epsilon element of x such that, okay, what am I thinking? It's not a lower bound, m plus epsilon is not a lower bound of f of x. So there's something in f of x that's bigger than this. How did we get something in f of x? It comes from an input value. So there exists this piece of epsilon element of x such that m plus epsilon, so it's not a lower bound, so I should say it this way, f of piece of epsilon is going to be less than m plus epsilon. And of course, this is bigger than m. Bigger than or equal to m. Little m. Okay? Little m. What this tells us then, for every neighborhood of m. Okay, so we're talking about every neighborhood of m. Okay, let's talk about this. This is in R, and every one of them, every neighborhood has a radius. Well, the radius is positive. We're talking about for all positive numbers here. There's going to exist something in f of x. That's a piece of epsilon. That intersects that. It's going to be contained in that neighborhood and intersects f of big X. And that's going to give us that m is, or little m is a limit point of f of big X. So let me write that up. So we're looking at a neighborhood of m. This contains a point big F of x that is not m. Okay, I have to go back. Okay, I made a mistake. So let us go back here. Okay, here I've got less than or equal to. So here, let's go back here for a second. I'm going to change that to less than. And how do I'm going to change that? I'm going to say, assume little m is not an element of f of x. If it is, we're done. Okay? Because that's what we're trying to show. So what if it's not? Then we get this. We get the less than instead of less than or equal to. I'm sorry about that.
Okay, so what this says then, so script M is a limit point of f of big X since f of big X is closed, then little m has to be an element of f of big X. So that's what we got. So let's see. So that means it has to be an element, because our assumption has to be wrong. Okay, there exists a Q element of X such that f of Q is equal to little m. And that's what we wanted to show. Okay, the next thing we want to do about compactness has to do with the inverse function. So let's get started with that theorem. Suppose f is a continuous one-to-one mapping of a compact metric space compact metric space onto, that's important, onto a metric space Y. Then the inverse mapping f superscript minus 1 defined on Y by the inverse of f of X is equal to X, okay, is a continuous, and that's the important thing I'm talking about here, is a continuous mapping of Y onto X. So here's the proof. We're going to let F be a continuous mapping of X, of a metric space, I should say. We'll give it a name, call it X, and then onto I made a mistake in this statement of this theorem. No, it's over on that other side. But onto Y and is 1 to 1. Okay, so it's 1 to 1. We want to show that this inverse function is continuous. The way we're going to do that is talk about inverse images of this inverse function of open sets and show that they're open. So it's continuous, I should say, from y, and then we also need to show that onto x. Okay. We will show continuity by letting u be open in x and showing the pre-image like this of u is open in y. Okay, that looks a little confusing. Okay, now here's what I want to tell you. That f inverse, the pre-image of f inverse of x is equal to f of x. That's what I want to show. So let's go through this. Why is that true? So in brackets, I'll write it y. As the pre-image, or the inverse image of the inverse function acting on x, okay, it's equal to a set. X, little x is in big X. Okay, it's a, if you will, output value for the inverse inverse function. And so, what the inverse image of the inverse function acting on x is, it consists of input values for the inverse function, which are y values, if you will. This is equal to a set of little y values that are in y, such that f inverse of y is equal to x. Okay, so since f is onto y, there exists a y element of y such that f inverse of y equals to x. Okay? So here I was taking a look at an x, little x and big X, and we were talking about the inverse image of the inverse function of it. And so there's something that is sent by the inverse function to that particular x because f is onto it. Okay? So this set is a non-empty. Since f is 1 to 1, there exists only one y such that f inverse of y is equal to x. Thus, x is equal to f inverse of y. So, f of x is equal to y. All right, that's what we have. That ends it. Now, the next thing that we want to show is that f of u, when I said that ends it, that ends showing that the inverse image of the inverse function acting on x is f of x. There's only one y here. That's the inverse image of the inverse function acting on x. And it's just this f of x. Okay. So now we want to show that f of u is open this work translates into what we need to show is that f of u is open in y. Okay, so remember we were trying to show that f inverse, or I should say, the inverse image of f inverse of u is open in y. But this f inverse image of f inverse of u is nothing more than f of u. Okay, that's what this work here justifies. Okay. Or I should say as. Those are the same. So we just need to show that this is open in y. Okay. Now, u was open in x. Okay. So, u complement is closed in x. Since x is compact, then u complement, being a closed subset of a compact set, it is compact. Since f is continuous, it's on x, but that means it's continuous on u complement. Okay? Then f of u complement is compact in y because the continuity maintains compactness. Okay. 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 So we know that compact sets are closed sets. So f of u complement is closed in y. Okay. Now remember what we wanted to show. We wanted to show that f of u is open. Okay. And so we want to make the claim that f of u complement is equal to f of u, take the complement of that. So let's write up that mechanics claim. So wait a second. So wait a minute, we have something for a second. The f of u complement is closed in y. So let me say this. So that means, so before I write the claim, f of u complement is open in Y. So here's what we're playing. Here's the F of U complement is equal to F of U. Okay, so that's what we'll prove. Let's work on that. Here's the proof of planes. We'll let Y1 be an element of F of U complement comp. I want to show Y is an F of U. Okay. Okay, so then that means that since Y sub 1 is in this complement of this set, that means that Y sub 1 is not an element of F of U complement. It's not an element. Okay. So since F is onto, there exists an x sub 1 element of x such that F of x sub 1 is equal to y. So equal to y sub 1. Y sub 1 is in big Y. And so there's something that's sent to it from big X by F. Okay? So this means that F of x sub 1, which is equal to y sub 1, and y sub 1 is not in here, so this is not, F of x sub 1 is not an element of F of U complement. Okay. Then that means x sub 1 is not an element of U complement. Okay. Because if it were an element of U complement, F of it would be an F of U complement. So what does that mean? So that means that x sub 1 is an element of U. So that means that F of x sub 1 has to be an element of F of U. So that means that Y is an element of F of U, and that's what we wanted to show in this direction. And so we have that F of U complement is contained in F of U. Now, we let y sub 2 be an element of F of U. Then, there exists an x sub 2 element of x, but in particular U, such that F of x sub 2 equals to y sub 2. Now here, since F is 1 to 1, then x sub 2 is the only element of x, such that F of x sub 2 equals to y sub 2. So what this says is y sub 2 cannot be an element of F of U complement. Okay? There's nothing in U complement that's sent by F to y sub 2. Okay? Thus, that says y sub 2 is an element of F of U complement's complement. Okay. So that says that F of U is contained in the set of F of U complement complement. And that ends the proof of claim. Okay? Ends proof of claim. So that says that f of u is open. And that's what we need to show. That's almost all of what we need to show. So f of u is open, and thus f inverse is continuous. The last thing we need to show is that f inverse is onto x. Okay. So here, note f inverse of y is onto x as for each x in big X, f of x exists in y. Okay. Since f inverse acting on f of x is equal to x, x is an element of f inverse of y. And so we've just shown that f inverse of y is equal to x. We've just shown that really big X is a subset of f inverse of y. And we know f inverse of y is contained in x. Okay? So that gets to this. All right, I want to conclude today by talking about a different type of continuity for a function, and that is uniform continuity. So we'll get this definition on the board, describe the idea just a little bit, and then next time we'll start off with some examples of uniformly continuous functions, and then have some theorems about it. This ends this proof. So here's the definition. We let F be a mapping of a metric space X into a metric space Y. We say that F is uniformly continuous on X if for each epsilon greater than 0, there exists a delta bigger than 0, such that the distance in Y between f of p and f of q will be less than epsilon, and that's for all p and q in X, with the distance right here in X between p and q is less than delta. That's its definition. Let me write up what. Let me say something. You know, when we talked about just continuity, we talked about continuity at a point and then continuity on a set. And when we talk about continuity at a point, it looked very similar. to what we've written here, there exists, for each epsilon greater than 0, there exists a delta such that the output values, f of x between the output, the distance between the output values, f of x to f of p would be less than epsilon as long as the input values were close enough to p within delta units. That's what we have for continuity. Here, the delta could, in that situation, the delta could depend on the p, the point at which we had continuity. Here, for uniform continuity, what we're saying is no matter what epsilon you give me, there exists a delta such that as long as the input values are close enough to each other, the output values will be very close to each other. And this delta will not necessarily depend on the point of interest. And let me write that up and we'll say that's enough for today. So, and here's my comment. The difference, between uniform continuity on x and continuity on x is that for uniform continuity, for each epsilon greater than 0, there exists a delta that depends on epsilon only. Whereas for continuity on x, for each epsilon and p element of x, there exists a delta that depends on epsilon and possibly p. Possibly p. So that's the difference. We're going to illustrate that difference through examples next time. Thank you very much.